Let's talk about acids and bases in PGY 2020. So, acids and bases. Well, really, what is an acid? We know an acid is a compound that disassociates in water to give us hydrogen ions, while bases give us hydroxide ions. So, atoms can either gain or lose electrons to form ions, and such a process when atoms lose or gain electrons to form ions is called ionization. So when an ionic compound such as sodium chloride dissolves in water and then their ions get to disassociate, that is called disassociation. So different from ionization. Ionization is losing or gaining of electrons to form an ion, while disassociation is an atom breaking to form ions. All right. So now, water can also disassociate to form these different ions. Actually, water is able to undergo what is called auto-ionization or self-ionization. Now, when water ionizes, it's going to form an hydroxide ion and an hydronium ion, right? The H3O plus, which is hydronium, and the hydroxide. Or apart from hydronium, it might form hydronium or it can form just hydrogen ion. Now, for the hydronium ion to be formed, it has to undergo an addition with its own. So, what I mean is, you have got one water molecule, let me use different colors, and then you get to add to another water molecule in solution. So one of these is going to act as a base, and then the others, and as I remember, a base supposed to be that one which gets to do what? So a base is going to give a proton to the other one. Okay, a proton in this case. So what is going to happen is that, let's say the red one is donating a proton to the blue one. So the blue one will become 83O plus, and then the red one is going to remain as a hydroxide. So what we are seeing, this thing which has been formed is the hydronium. This one is acidic, and then the hydroxide is a base. So what happened is that this water lost hydrogen. So this one, a proton donor, is called an acid, right? And then a proton acceptor is called a base. So in here, we are able to form what we call acid base conjugates, right? So what is an acid and a base? How do they differ? So an acid and a base basically differs from each other by one hydrogen. So if you look on the reactant side, here you have got this water and then this one. So you have got H2O slash H3O plus. So the one which has got a lot of hydrogens is called a acid, and then the one with lesser hydrogens is a base. Same with these other ones in red, you have got H2O, and then on the product you have got OH. So the one with more hydrogens is going to be the acid. So meaning this is going to be the acid, this is going to be the conjugate base. So the conjugates just differ from each other by one proton, which is hydrogen ion. Right. So basically that is water. Now water can also undergo self-ionization or auto-ionization. So this water just breaks by itself. In this case, what you're going to see, you're going to form hydrogen ion and hydroxide ion. So basically the concentration of hydrogen ion is supposed to be equal to, or is taken to be equal to, the concentration of the hydronium ion in solution. Right. So the pH scale is the one which is going to be used to determine whether a solution is going to be acidic or basic. So pH is just defined as the negative log of the hydrogen ion concentration. That is pH. And then, so if I'm talking about certain concentrations, so let's say I have got a concentration X, I can find what is called px, and that is basically given by negative log of this same concentration of X. If I'm talking about the concentration of hydrogen, I can find p hydrogen. That is what is called pH, and that will be negative log the concentration of hydrogen. If I've been given OH, I can find what is called POH, and that is given by negative log of hydroxide concentration. If I've been given Ka, I can find what is called pKa, and that is just given by negative log of Ka. So negative log of something will give you the P of that something. Negative log of H is pH, just like that. Now, when we are talking about pure water, which is at 25 degrees Celsius, the concentration of hydrogen ions is equal to the concentration of hydroxide ions at 25 degrees, pure water. And that concentration is 10 to the power negative 7. And so if you punch pH is going to be negative log of 10 to the power negative 7. That is going to give you pH being equal to 7. If you wanted, also you can find POH. That is going to be negative log, because the hydroxide concentration is also 10 to the power negative 7. That will still give you 7. So we see when we get to add the pH and the POH, what you get is 14, and that is called PW. All right, that is the dissociation constant for water. Okay, so acidic solutions are going to have a pH which is less than 7, and then basic solutions are going to have a pH that is greater than 7, but it shouldn't be above 14, because when you get to add those two, it's supposed to give you 14. Most biological fluids in the body, they get to have a pH from 6 to 8, meaning that they should be nearly neutral. Okay. Strong acids and bases refer to those compounds which dissociate to form ions when dissolved in water. Okay, so weak acids like the acetate ions, also acetic acid, even this one, hydrogen fluoride, these are weak acids. What happens is that only partially dissociate in water. So the dissociation, we're going to see it like this. Now, for strong acids, they fully dissociate. For example, hydrochloric acid, you're going to see just the arrow going like that. It will barely come back. So coming back, you just show a small arrow like that. So we're going to have hydrogen ion and then chloride ions. Okay. So the strength of an acid and a base depends on how much it disassociates. The more it disassociates, the stronger the acid or base. Now, in order to quantify the relative strength of acids, we can look at what is called the acid dissociation constant to see which one is stronger than the other. So the acid is given a generic form of H with an A. So this A can be anything. It can be chlorine, then we're going to have hydrochloric acid. It can be F, hydrogen fluoride. It can be anything. So that this is just the generic form for a monoprotic acid. The general form for a diprotic acid like that, and then we can have a triprotic acid. These are called polyprotic acids because they have got more than one protons. So if this one undergoes ionization, because acids, we know that they are able to ionize in water. I can either react it with water or just undergoing ionization by itself. Now this one is a weak acid, so it's going to form like this. Or I can react it with water, then we are going to have Ha plus water, and then we are going to have what is going to form like this, H3O plus, and then plus, okay, we are going to have now A minus here. So basically this hydrogen has been taken by here. Okay. So this one which is here is a conjugate base of this acid. This one is a conjugate acid of this base. In this case, water is acting as a base. Now, because water is a liquid, in the expression for Ka, we don't include this. So basically, it's going to be the same as this one. Remember, we said the concentration of hydronium is equal to the concentration of hydrogen ions. So then what are we going to form here? So for the Ka, which is acid dissociation constant, you simply get the concentration on the product side, that is Ha, okay, and then multiplied by the concentration of A, and then you divide by the concentration of what is on the reactant side. So this is how we are able to determine, or this is the expression that gives us what we call the Ka. Okay. So acid dissociation constant, which is Ka, is quantitative measure of the strength of an acid. The larger the value for Ka, the stronger the acid, since the acid has largely dissociated into its ions. Now, because the numeric value of Ka of especially weak acids is very small, you are going to mostly express it in terms of pKa. Already said, if you have got Ka, you take the negative log of that Ka, then you are going to have pKa, right? Now, for pKa, it is not like Ka. When pKa is small, this means that the acid is very strong. If pKa is big, that means that the acid is small because we have got a negative there, right? So it is opposite in that way. So for example, acetic acid has got a pKa of 4.7, and then lactic acid has got a pKa of 3.8. Now, using these two values, we are able to determine which one is going to be stronger than the other. So in this case, lactic acid is stronger than acetic acid. Why? Because it is the pKa for lactic acid is smaller than the pKa for acetic acid. But if we are comparing the Ka values, the Ka for this one is going to be bigger than for this one. Okay. So this is an example. Acetic acid is a weak acid with an acid dissociation constant Ka of 1.8 times 10 to the power negative 5. We want to calculate the pKa. So simply we know that pKa is given by negative log of the Ka. Then this is going to give us negative log Ka, that is 1.8 times 10 to the power negative 5. And this is going to give us about 4.7. All right. Now, when you have the pKa and you also have the pH, you are able to give a relationship between these two quantities. And how do you give the relationship between these two? The relationship between the pKa and the Ka can be given by the Henderson-Hasselbalch equation. So that just comes from what we have here. Now, let's derive how do you get the Henderson-Hasselbalch equation. So the generic form of an acid is Ha. This can dissociate, and we are going to have A plus, and then H plus, and then we are going to have A minus, right? So from here we said Ka can be found by getting the concentration on the product, that is the concentration of hydrogen ions. We multiply by the concentration of the A. Now, I'm supposed to raise it to their coefficient. So if I had x in front here, then I'm going to put it to the power x. But we don't have anything like that. And then we are going to divide this by the concentration of the Ha, which is basically the acid. Now, from here, I'm going to split these terms. So I'm going to have Ka being equal to, I'll say concentration of hydrogen ions, and then I'll say A minus divided by Ha. Okay, from here I'm going to introduce negative log on both sides. So let me have negative log this side, and then let me also put negative log this side. This is supposed to be in brackets like that. Now, negative log of Ka, we already said this is going to be pKa. And then we know that for the rules of logarithms, if I've got log of AB, this means that we add log of A plus log of B, meaning that there was an addition. So I can actually split this. So I'm going to have this being equal to negative log of A, H in this case, plus. Now, because this log is negative, it means that these two are all going to carry negative. So this is going to be negative log of H minus divided by HA. From here, what are we going to have? We know negative log of hydrogen concentration. So this is going to give us pKa being equal to pH. And then minus log concentration of H minus divided by HA. Now we already said this is the acid, and then this is going to be the conjugate base. Okay. So what from here I can take this term, this other side. So we're going to remain with pH being equal to the other side, we're going to have pKa plus, if I take this term the other side will become positive, plus log. Now A, we've seen this is a conjugate base, so I can simply say base over HA, that is acid. So this is the Anderson-Hasselbalch equation. pH is equal to pKa plus log concentration of the base over the concentration of the acid. Calculate the pH of a buffer solution made from 0.20 molar of this acid and 0.50 molar of this one that has got a pKa of, so the acid pKa is 4.7. So how are we able to determine this? Now we know that pH from the Anderson-Hasselbalch equation is equal to pKa plus log concentration of the base divided by the concentration of the acid. This is going to give us, for pKa we've already been given 4.7, and then log acid. Now I already said that acids and base only differ by a proton. Acids have got one proton more than the base. So meaning that this is going to be the base and then this is going to be the acid. For the base, the concentration is 0.50. The acid, the concentration is 0.20. So simply punch that on our calculators. So let me start with 0.50 divided by 0.20. The answer I get, and then I'm going to say log of that answer. So this is going to give us 4.7 plus 0.3979. And then the answer that we found here, we are going to add the 4.7. This is going to give us about 5.0979, which we can simply give as 5.1. So this is going to be the pH of the solution then. Let's consider this one. A buffered solution contains 0.5 molar acetic acid. Okay, there. With this Ka, okay, the Ka, it's the same as the previous one. Okay, for this one, we are given the pKa. Now, this one, we've been given the Ka. Now, the way the number is, let me just write it here because I just copied the question like that. So, the Ka for acetic acid is 1.8 times 10 to the power negative 5. 1.8 times 10 to the power negative 5. Okay, that's the one. Now I want to calculate the pH of the solution. Now from what we've been given the acid, okay, and then we've been given this one. The sodium doesn't participate in the reaction. It's just there to hold this conjugate base. If I remove the sodium, meaning I'm going to have C2H3O with a minus sign because the sodium is just there to neutralize that sign. So basically what is happening is when we have got the acid, which is H2 and then C2H3O2, this is disassociating, and what are we forming? We are forming that conjugate acid that we are able to see. So even this one, the H2, I think this was also, okay, this is just HC2. This is not H2. So what we are going to have is the hydrogen is going to be low. So we're just going to have C2, H3, and then O2. This will remain with a minus sign and then also hydrogen ion here. When we are talking about the Ka, we know that Ka, okay, now let me use what we call an ice diagram, because when you're finding the pH, you use the concentration of the acid or the concentration of hydrogen ion at equilibrium. So the ice table will start with I, which is the initial concentrations which are given. The concentration of the acetic acid has been given as 0.5. The concentration of the conjugate base has been also given as 0.5. We don't have any hydroxide, meaning that is 0. And then there shall be a certain change because as the reaction is happening, reactants are converted to products. So this is going to change by negative x. Negative because it is reducing, while the concentration of these two are going to increase by x. So if there was a 2 here, I would say the concentration would increase by 2x. Okay. And then at equilibrium, when we reach equilibrium, what we're going to see for the concentration of the acid is going to be the initial minus that change, and then for the base here to be the initial plus that change, and then for the hydrogen is just going to be x then. So 0.50 minus x is going to be approximately just equal to 0.5. And the reason for that is there is basically a very small change. If we look at the Ka is very small. Since the Ka is very small, meaning that even the change in concentration is going to be very small. So this value is approximately just going to be equal to 0.50. This one also will be approximately just equal to 0.50. So meaning to find the Ka, okay, of course we've been given the Ka, but we want to determine the concentration of hydrogen ions for us to be able to determine the pH. So Ka is given by the concentration on the product at equilibrium. We have got 0.50 and then we have got X. We'll divide that by the concentration of the reactants at equilibrium, that is 0.50. So what we are going to just find is X is going to be equal to Ka, and we know that Ka is 1.8 times 10 to the power negative 5. And what is X? X is the concentration of hydrogen ion. And you know that pH is given by negative log of hydrogen concentration. So then this is going to give us negative log of 1.8 multiplied by 10 to the power negative 5. Let's punch that. Negative log of 1.8 times 10 to the power negative 5. That is going to give us 4.74. This is going to be the pH. So this is if we want to use the formula. I mean, if we want to use this method of getting to determine the quantity that we've not been given, which is the concentration of the hydrogen. But if we want, we can simply use the Henderson-Hasselbalch equation to be able to find also the pH, because what we've been given is a buffer system. I mean, this is of course a buffer because we have got the acid and its conjugate. That is what we call a buffer. So now, how do you get to calculate using the Henderson-Hasselbalch equation? pH is given by pKa plus log the concentration of the base over the concentration of the acid. And then pKa is found by negative log of Ka. The Ka has been given as 1.8 times 10 to the power negative 5. And then plus log. Concentration of the base is 0.5. Concentration of the acid is 0.5. 0.5 over 0.5 is the 1. The logarithm of 1 is 0. So we just have negative log of 1.8 times 10 to the power negative 5, which is 4.74. So this is it, and this is how we are able to determine this. Don't forget to get to subscribe and get to follow as we get to produce more tutorials.